What's up, guys? So today we are going to be continuing a lesson that we did in a previous video on curve sketching. In the previous video, we used the first derivative to find intervals of increase and decrease of our function, and then we also used the original function to find information like vertical asymptotes, horizontal asymptotes, and the y-intercept. So in today's video, we're going to be focusing on the second derivative and the information that we can get from that. Now, if you guys missed the first video, that one's going to be really key to understanding a lot that's going on here. So I definitely recommend you checking that out. But if you've already watched that video, it's time to go forward. So for our second derivative, that gives us information about the concavity of our function. Now, concavity is also defined almost as the slope of the slope. So a positive second derivative, since that's the derivative of the first derivative, right, where the first derivative calls or talks about the slope, a positive second derivative means an increasing slope. A negative second derivative means a decreasing slope. So an increasing slope might look something like this. Maybe it starts sort of like this and then gets progressively more positive over time. A decreasing slope might start something like this and then get progressively more negative over time. Right, and so you can kind of say maybe this was -3, -2, maybe 0, 2, 3, something like that. So the slope is always increasing. And then this one, maybe this starts at, +2, 1, 0, -1, -2, so always decreasing. That's the idea of increasing and decreasing slopes. And so what we say is if a function has a curve which sort of looks like this first one, we say that that function is concaving upwards, so it's kind of curving upwards. And similarly, if a function has a curve like this second one, we say that's concaving downwards. All right, so what we're looking for then is where our second derivative is positive and where it's negative, and that's going to tell us about the concavity of our function. So first thing we want to do then is take our second derivative. So to do that, we're going to be using the quotient rule. So if I define this upper function here as g of x and this bottom one as h of x, g prime of x would be -4. H prime of x is going to be 2 times x squared minus 1 times the derivative of the inside bit, which is 2x. And that'll actually simplify to 4x cubed minus 4x. All right, so if we solve our derivative overall, and if you have any issues with the quotient rule, definitely feel free to revisit the quotient rule lesson in a previous video. But this second derivative is going to turn into the derivative of the top function, which is -4, times the bottom function, so x squared minus 1 squared, minus the top function, which is -4x, so I'm actually going to write that as plus 4x, times the derivative of the bottom function, which we found to be 4x cubed minus 4x. And then all of that is going to be divided by the bottom function squared. So x squared minus 1 squared, and then squared again, is going to be to the power of 4, because those exponents would just multiply together. Okay, so now we really want to simplify this, because I don't think it's at all obvious right now what values of x are going to make that numerator 0. So this is going to turn into -4 times x squared minus 1 times x squared minus 1. We sort of expand that. Plus 16x to the 4 minus 16x squared. And all of that is going to be divided by x squared minus 1 to the power of 4. All right, we simplify that again. On the top, if we sort of collect all of the terms there, we're going to get -4 times x to the power of 4 plus 8x squared minus 4. And then we're going to have plus 16x to the 4 minus 16x squared. And all of that is going to be divided by x squared minus 1 to the power of 4. Okay, so from here, we're going to collect like terms on our numerator. So that's going to net us 12x to the power of 4, right? The 16 minus the 4, minus 8x squared, right? Plus 8x squared here, minus 16x squared here. and then minus 4. And then that's going to be divided by x squared minus 1 to the power of 4. All right, still not super easy to see where our numerator is going to equal 0, so we're going to simplify this a little bit more. First thing we can do is factor out a 4. So this is going to be a 4 out here, right, because 12, 8, and negative 4 are all divisible by 4. Now to make this into a form that we're more comfortable with, I'm going to make a little substitution. I'm going to say let maybe a equal x squared. And what that's going to do is instead of x to the 4, we'll have a squared. Instead of x squared, we'll have a. And then it's not going to change our constant in any meaningful way. And so this would technically be a minus 1 to the 4 now. All right, now this numerator is looking a little bit more reasonable, or at least it's something that we've seen before, right? It's just kind of a quadratic. So if we want to find where this numerator is equal to 0, what we're going to need to do is factor it out. And so let's try factoring this. So I'm going to look for 2 multiples of 3, maybe 3 and 1, and then 2 multiples of negative 1, so maybe 1 and negative 1. 3 times negative 1 is negative 2, or sorry, negative 3. Getting ahead of myself there. And then 1 times 1 is going to be 1. And if you add those up, you get negative 2, which is the same as our b value in the quadratic, which means our factors are going to be 3a plus 1 times a minus 1. Okay, so our second derivative is going to be 4 times 3a plus 1 times a minus 1 divided by a minus 1 to the power of 4. Now if we substitute back in our values of x, we get our second derivative is going to be 4 times 3x squared plus 1 times x squared minus 1 divided by a minus 1 to the power of 4. And actually, sorry, not a, x squared minus 1 to the power of 4. Okay, so what happens here, not very satisfying after going through all that work, but the x squared minus 1 can cancel with this exponent here, which will reduce to a 3, and we're just left with 4 times 3x squared plus 1 divided by x squared minus 1 to the power of 3. All right, so where does this equal 0? Well, if you guys remember, that's the same as asking where the numerator equals 0, because the denominator equaling 0 will actually give us an undefined value. So if we're just trying to find where the function equals 0, we're looking at our numerator. Now, 3x squared plus 1 equals 0 is actually going to give us an imaginary or complex solution. And that's because you'll find you end up with x is going to have to equal plus or minus the square root of negative a third. And the square root of a negative number does not give any real solutions, which means we're not going to have solutions for the numerator equaling 0. However, we still want to use the values of our vertical asymptote as x equals 1 and x equals negative 1. And that means the only points on this function where we're going to be switching concavity, since there was no spots where the numerator was equal to 0, is going to be at x equals 1 and x equals negative 1. All right, so now what we want to do then is we're going to test values around 1 and negative 1 to determine which direction our concavity is in each of those intervals. Okay, so some values around 1 and negative 1 are, we'll do when x is less than negative 1, maybe we'll try x is equal to negative 2. For x is between 1 and negative 1, maybe we'll try x is equal to 0. I always like using 0 when we can. And then when x is greater than 1, maybe we'll try using x equals 2. Okay, so for x equals negative 2, if we plug that into our second derivative, we get 4 times 3 times negative 2 squared plus 1 divided by negative 2 squared minus 1 cubed. On our numerator, that's going to be 4 times 13 divided by 4 minus 1, so 3 cubed. Now we don't even have to simplify this any further to determine that this is going to be a positive value because every number in our expression now is positive. So we're going to say this is positive, which indicates that our function is concave up when x is less than -1. All right, now we're going to try x equals 0. So our second derivative is going to be 4 times 3 times 0 squared plus 1 divided by 0 squared minus 1 cubed. On our numerator, this is going to give us 4 times 1, so 4, divided by -1 cubed, which is -1, and that's negative. And so that means our function is concave down when x is between -1 and 1. And then for our last test, we're going to try when x is equal to +2, where our second derivative is going to be 4 times 3 times 2 squared plus 1 divided by 2 squared minus 1 cubed. This is actually going to work out to the exact same thing as before because the x values in our expression are all being squared, and 2 squared is the same as -2 squared. So this will once again be 4 times 13 divided by 3 cubed, which is again positive, and that means that y is going to be concave up when x is greater than 1. Okay, so we've got all of our intervals of concavity. So let's see if we can finally graph this function using that information. So what we found there was that from here and below, so from -1 and below, our function is concaving up. Between 1 and -1, we found that our function was concaving down. And from 1 and beyond, we found that our function was again concaving up. Okay, now what that means is to get to this y-intercept here, our function has to be increasing and concaving down. So rather than looking something like this, it's going to look something like this. And then from there to the next vertical asymptote, it's once again going to be concaving down and decreasing. So rather than looking like this, we know it's going to be looking something like this. In this top right quadrant, it's going to be concaving up and decreasing. So rather than looking like this or like this, we know it's got to be concaving upwards, so it's going to look something like this, and we know that it's going to be approaching that horizontal asymptote. Now we actually know that it's in the upper right quadrant without even plotting any points, because there's no way the function is cutting through this horizontal asymptote, which means if the function is decreasing, there's no way that it's starting like this either. So the only way that the function could be decreasing and concaving up is if it started in the top right quadrant rather than from down here. Okay, and then in the top left quadrant, once again, our function is increasing and concaving up, so it's going to be looking something like this. All right, now I think most people, if you're familiar with rational functions, you could have predicted those intervals of concavity. But in general, if you have a function which is maybe less intuitive and you're not sure what the graph looks like, this is a really good tool to get a better idea of the behavior of the function. All right, but that's it. We have our graph using the second derivative to find concavity, as well as the first derivative to find intervals of increase and decrease, and then the original function to find maybe special points like where asymptotes occur and where intercepts occur.